Who am I? I'm Thomas Schütz. I'm an aerospace engineer with a focus on embedded system software and architectures and tool development. And I'm founder and CEO of PROTOS. So we're talking about state transition testing today. Why do we want state transition testing, or in general, why do we want to test? The biggest problem is that we test too late in the process. We need to test and learn earlier. And whatever we do is we try to bring the tests more to the developer, to the desktop of the developer. We need to get a very early verification of what we do. That's a very important step. And state transition testing helps us to get a very big coverage very early in the process. So first question is, how do we derive test cases? I'm sure you all know a lot of different ways to derive test cases. You can use use cases, requirements, and think about how could I test this requirement. There are more formal approaches like equivalency classes, border or boundary analysis, or also things like a classification tree. One very nice method, I think, is state transition testing. So we are focusing today on state transition testing. So always, what do I want? So what are my requirements, and how do I derive test cases from this, from what I want? So how do we define coverage? That's another question related with some test methods. The typical coverages are code coverage, for example, C0, C1, and so on. Feature coverage, requirement coverage. So do I have a test case for all my requirements, and so on? And two coverage methods we want to focus on today is the state transition coverage, end switch and transition coverage, for example, and the data coverage. So I'll explain later what this is all about. So let's start with the state transition test. So what is a state transition test? A state transition test, to start with, is a black box test. So yes, you have state transition diagrams in your embedded software, but it's not about them. It's about describing the expected behavior of your system or your component or your integration block as a external behavior, as an expected behavior. And from that expected behavior, we can derive test cases. So it's a black box test. Every transition in such a state transition diagram is a test step. So wherever I go, I execute test steps on the way. Every pass from initial to end is a test case. So every pass is a test case. And the goal is to at least cover all the states and all the transitions in this diagram. So to touch every pass at least once. Better is a higher pass coverage, in-switch coverage, for example, for combinations of different passes or parts of your passes. And for higher coverage, automatic code generation is very useful if not needed. It's hard to get right for the higher coverage on a piece of paper. So what's the coverage, for example, here? Every path from initial to end, I said, is a test case. So for example, that's one test case, next test case, and so on and so on. And in the end, you want to cover at least all the states and all the transitions in your state transition test. So it's a very elegant way to derive test cases. Let's start with a piece of paper. You can do state transition testing on a piece of paper. So let's start with a typical little example with a motor control. At the beginning, you start with the motor off. That's the first step in your test case. Then you can switch the motor on. And now you can decide whether to change the speed or to brake. Yeah, why not doing both paths? So let's split it up here and go both ways. And after a certain while, you go together again and you want to change the mode. So change mode to 1 and change mode to 2. So this is the design of my state transition test. It's a very simple state transition test, but it's good to show what we do. So now we derive the test cases. So we select one path through the state transition diagram and step by step create a test case for that. And we create the next test case 2, that takes a different path through my system or through my test case here. In this case, I already have a complete transition and state coverage. That's really nice. But what if I want to combine paths? For example, what I did not cover is the combination of brake and mode 1, or the combination of change speed and mode 2. So the red and the green path are not covered by those two test cases. So I need more test cases. And also eventually I want to bring in loops. I want to restart my system again. I want to do things several times in a row. And that's really hard to get right on a piece of paper. So if you need higher coverage, so you have bigger systems or you want cycles, then it's really nice to have something else. So that's why we developed a state transition tests with a generator included in our little miniHIL test system. And you design your state transition diagram in a tool, and then you generate all the needed test cases for a certain coverage. You generate this directly from the tool, and those test cases are directly executed in our little hardware in the loop system, for example. Could also be used for a unit test or something else. So in general, the method is pretty generic. Depending on what you want to do with it, you can use it for different test setups. So that's how the code generation here works. And now let's have a look at the coverage I mentioned at the beginning. So let's start with the end switch coverage. So it's a path coverage. I already explained it a little bit in the graph before. The goal is to have a complete state transition coverage, at least. Again, it's a black box coverage. It's not about the state transitions in your system under test. It's about the test system, the coverage of your test paths. And it would be better to have a complete path coverage or at least a higher path coverage. So the end switch and transition coverage is defined with zero switch, one switch, end switch. So for example, zero switch would be this. So every path is, or every step, every state and every transition is covered once at least. And one switch would be the combination around a state. For example, every state has incoming and outgoing transitions. And for example, in this case, the change mode, you have incoming transition here and here. So 2 incoming transitions and 2 outgoing transitions. So you have at least 4 paths you need to cover locally here, this combination. That's the idea of end switch. Is a really elegant metric because it does not explode. It does not produce too many test cases, but it produces a lot of relevant test cases. Next step would be the data coverage. It's also something you can do with state transition testing. The goal is to achieve a coverage for data combinations. The word here is, the metric here is n-wise coverage. So maybe you know pairwise, that's for 2 parameters, n-wise is for n parameters. An example would be here parameter A and parameter B. Every parameter has 3 different values. In this case, for example, 3 combinations or 3 values for your equivalency classes, and the combinations from those 2 parameters are 9 combinations, 3 by 3. So if you want to define this with a state transition test, you can define a state transition test, and in the first step you define the first 3 parameters or the first 3 values for the first parameter. In the second step, the 3 values for the second parameter, and the code generator generates the combinations of all those paths. So you get 9 different combinations, and the test after that is run with 9 different combinations. So it's 9 different tests. We also can combine the NWISE and the NSWITCH coverage. For example, the NWISE coverage for data coverage here. We start with the data setup, and then we continue with the path coverage. So now we can combine data coverage and path coverage, which is very effective to find a lot of errors. So why all the effort? It's a very nice method, I guess you've seen, but why all the effort? What can I do with it? So one very important thing about state transition testing is to find sporadic errors that are really hard to detect and debug. So something that happens once a year in 2 of your machines, for example. You have hundreds of customers, but 2 customers have a problem. So that's really hard to detect, and it's really hard to debug. And by using state transition tests, you can find a lot of race conditions or potential race conditions, and those race conditions very often lead to those sporadic errors. So you also can find side effects. You go many different paths, and you might experience some side effects, instabilities and things like that. So by doing that, you can run stress tests, you can run performance tests, and you also can run long-running robustness tests with many different test cases. So if you run the same 50 test cases over and over again, this might not give you a really good idea about your robustness of your system. But if you generate, I don't know, 100,000 or 50,000 or 5 million different test cases, this might give you a much better view on the robustness of your system. It's much more likely that you break your system while running those combinations. So I'm going to demonstrate you a little bit how we do this in our tool set. I'm using our miniHIL hardware platform and software platform. The idea is to test the system under test. That's this microcontroller. At the pins of the microcontroller, we connect those pins of the microcontroller with our test system, and on this side we simulate, for example, the motor or the environment your system is running against. So we do not need a real motor, we simulate the motor or a battery or whatever it is, and on top of that we put the test cases and we generate them. So let's have a look at what we do here on this side, because that's where the simulation and especially the test cases live, including our state transition tests. So the miniHIL test process starts with modeling. So we define models for the environment simulations and the test cases and the state transition tests as well. From there we generate C code, we compile it, we flash it. Then we execute the hard real-time tests on this miniHIL hardware-in-the-loop platform. In this case, that's an Oryx processor, for example, from automotive. Before we've seen an STM32 from medical devices or any kind of other systems. And when we run the test cases, we log the results so that you see as a developer or as a tester much better where the problem was if you have a problem. And we learn and iterate and go do the next step. Either we create a new system under test or we create a new test system iteration. So that's the basic idea. The demo I'm going to show you is a motor control system with a BLDC motor control. It's a block with block commutation and 3 Hall signals. So on this side, we simulate the motor. On this side, we have the motor control system. We also have a temperature sensor and so on. I don't go too much into details. And for example, that's the electrical level That's a look at the logging, at the signal logging when a test case runs. And here, for example, we can do things like we can change the speed, we can test the temperature stop, an error, or warning, a limp home functionality, and so on. Those are all little test blocks, test steps we can use to combine them in our state transition tests. So far our example. Now let's make a little demo. I'm going to start with a little state transition test here. That's our development environment. We have steps. That's just fake steps here. In our real state transition test, we have real steps. So they really test the motor or the battery or whatever it is. And now to elaborate a little bit on the test method, I'm going to use this little demo state transition diagram. So let's assume we want to add a test step. So let's add an additional state. That's state 1. So now I have an additional test state. And now I need to connect the initial state with the state 1. And of course, I have to end the test case. If not, you get an error. If not, the test will never end or cannot run. So now that's the simplest possible test. And of course, while going from initial to the state 1 or from state 1 to end, I want to execute a little test snippet. So every transition contains a little test snippet that tries to prove whatever you need to prove there. It triggers an action and it waits for the reaction. So for example, in this case, I prepared some dummy passes here. So that's a dummy action. So in this case, path 1. So let's have a look at what test cases we generate. I start the documentation generator or the generator, and let's have a look at what we did. So far we created one test case. That's test case 1. It's pretty clear. So now let's take different paths. Like let's take 2 paths to state 1. Again, I generate the documentation. Let's have a look at the documentation. And now we have 2 test cases. We are in switch 0. So still we have a complete transition and a state coverage. So now let's make it a little bit more complicated. Let's add another state, state 2. And from state 2, we go to the end. And from state 1, we go 2 different paths to state 2. So now we have this kind of system. Let's have a look at what happens if I generate the documentation and potentially, of course, the test cases also. But it's easier to see in the documentation here. So now I have path 1, path 2, path 1. And here I see I have covered all the states and all the transitions, but not a combination between path 2 here and path 2 here. So it's only path 2, path 1. So if I want that, I put the end switch coverage to 1 instead of 0. And we start again. And let's see what happens now. Now I have 4 test cases. So path 2 against path 2 and path 2 against path 1. So that's the idea of those end switch coverages. And to elaborate a little bit on the problem of cycles, I'm going to create from state 2 maybe a cycle back to state 1 because I don't want to stop my my test case. So I don't want to stop my test case so easily. I want to go back and test more and more. So let's generate the documentation again. And suddenly we see we have a couple of more test cases now. We need 7 test cases to cover for N switch 1. So now imagine you make the system bigger, then it gets much bigger. You get much more test cases, and it's really hard to get it right on a piece of paper. But please start on a piece of paper. That's always a very good method to understand and to derive test cases. So let's have a look at a real test case in a demo system, of course, but that actually really does something. So here I have a motor control system test. So I activate the UART, I request 3 different speeds. So they all run the same test case, but with different speeds. And here I have a different paths I want to cover. I want to go back, and so on and so on. So let's have a look what we can generate from that test case. From that test case, we generate for N switch 1, 15 test cases. Okay, so now let's run them. In order to do that, I'm going to go to my test setup. That's my hardware loop test system. And here I have all the PWMs, the Hall sensors, the digital IOs, serial interfaces, and so on. Here's the motor control, and here are the state transition tests that try to break the motor control. So let's run the test cases. This is, for example, a requirement-based test case. I want to test the motor control speed or the temperature limit, whether this works or not. And here in the state transition tests, I do a bit more combinations of whatever I want to test. So let's run the tests. I'm connected with the system. So now the tests are running. In this case, 15 state transition tests. If I make N switch 2, for example, I get 30, 40 test cases. And here you see what really happened. So that's what really happened in the motor control system while running the test case. So now let's break the system a little bit. I'm going to pull the plug while the tests are running. So now I'm going to pull the plug. Now something is going wrong. I fixed the test case again, or the test setup again, and now the tests have been run. So when I generate higher N switches, I can get much more coverage, combinatorial coverage for data or for transitions or for passes. Okay, so let's go back to our conclusion. So what can you do with state transition tests? You can make your software much more robust. You can reduce the effort to develop many test cases. It's a really nice method to do that. And in detail, you can you have a very good method to define test cases for path and data coverage to make your software more robust. State transition tests can be done really nice without tools if you do not overdo it. But for combinatorial test cases, modeling tools and code generators are necessary or recommended. You can do it manually, but that's a lot of effort. It's hard to get it right. Okay, so that's it from my side.